Okay. So, in the previous class we have already defined, means we have given one example of rolling a die. We have said that there are two events, which is called the event where the means top surface of the die will be showing me a even number, and that is called or odd number. Okay. So, that AO is called that it will be showing odd number, and then another event we defined, that is B, that the number it will be showing, that is less than equal to 4. Okay. So, we started evaluating the joint probability that P A0 or AO and B both are happening. Okay. And then from the frequency definition we could see that it should be this, where we have defined a conditional probability that a particular event has already occurred, means given that what is the probability of the other event happening, and PB, okay, multiplied by PB. This is something we could see. This is another axiom of probability theory, PAO intersection B. So, that is pretty much what mathematical theory does. The initial part you take it from experimentation. Okay. You build up the first few forms of axioms, and from there in a deductive logic, which we are doing now. Okay. So, you have given that definition, frequency definition to probability, and after that it is just deductive logic with which we are actually going forward. Okay. So, this is one axiom which is being derived from that frequency definition of probability theory. Okay. So, this is something we have already understood. Now, let us say that this AO, the event is independent of B. What do I mean by that? That is a very important definition in probability theory, that two events are independent. Okay. So, what do I mean by that? That means that occurrence of AO does not really depend on whether B has occurred or not. Okay. So, whenever we are trying to evaluate this N2, how many number of times AO will occur given B has occurred, even if I do not consider B, I will probably get the same number. If this is happening, that means I have no dependency for the probability calculation of this particular event on the previous event. I will give some example. So, basically in that case what I can say is PAO given B is independent of B, whether B has occurred or not, I will get the same number. So, I can write this as PAO, and immediately this formula turns out to be, that is a very important theorem of probability. If two of the events for which you are calculating the joint probability or the intersection, if both of them are independent, their probability just gets multiplied, probability of individual event gets multiplied. We will just give you some example and it will be very clear. So, let us take this, let us first give one example, one very simple example of this dependency. So, let us say I have a particular urn with two red ball and two black ball. Okay. So, I have this thing where I have two black ball and two, let us say two white ball. Okay. Now, if I can't see what I am picking up and randomly I pick a thing, there is a probability that it will be either red or it will be black. Okay. If me picking a ball is any of them is equally likely, then what should be the probability that I will be picking up, means let us say white ball, that should be half, because there are 2 favorable and there are 4 overall things. Okay. What is the probability that I will be? So, this is probability of picking white ball, probability of picking black ball should be also half. Okay. So, now I say I define 2 events. One is first time I will take out a ball, okay, and I see what it is, and then I put the ball back inside the urn, and next time again I take out a ball. Okay. So, the first time I am taking out, that is a random event, and second time I am taking out, that is also a random event. Let us call that A1 and A2. The outcome of A2, does it depend on the outcome of A1? Absolutely no, because I have replaced the ball. So, the experimental scenario goes back to the previous case. Okay. So, whether in A1 I have taken white or red, I have replaced the same ball, the overall means sample space remains the same. So, whatever again I will be taking out, if things remains equiprobable, I will be getting same probability. So, this A1 and A2, these two events are independent of each other, but suppose I do not do that. In the first experiment I take out something and I do not replace it. Okay. So, immediately what will happen, the probability will be now dependent on the outcome of the first event, because if I in the first event I have picked a white ball, then this balance will be little bit changed for the second experiment. There will be 2 black and 1 white. So, automatically P black will become 2/3 and P white will become 1/3. And if I in the first experiment I pick a black ball, then the reverse will be happening. So, now I can see my probability calculation or the overall event is dependent on the first event. Okay. So, this is where I say two events are dependent or independent. Okay. So, let us just for fun we go back to the same example we have taken. Sorry. Okay. Now, let us define this as my B, this as AO, this as AE. Let us try to see if I wish to calculate P AO intersection B. I first assume that they are probably independent. Okay. I still do not know whether AO and B are independent or not. We will try to derive this, okay, or try to see that, and you will see a very interesting case. So, suppose I assume that. So, immediately what will happen? Because they are independent, the probability theory according to our derivation, it says it should be this. Okay. So, what is probability of AO? That is actually 3 events divided by 6 events. So, that should be 3 by 6 or 1 by 2 into what is probability of B? That is actually 4 divided by 6. So, that is 2 by 3. So, it is 1 by 3, right. If I take them to be independent, I might be wrong, I will try to verify that. Now, I will do the right calculation. If I do not have knowledge of independency, I will do a right calculation. So, which says probability of AO given its B into probability of B, this was the actual definition if they are not independent. So, I still do not know whether they are independent or not. So, this should be the right calculation, this is more generic. So, let us now try to see what is the probability that if given B has happened, what is the probability that AO will be happening. So, given B has happened, how many cases are there? I will be restricted already. Okay. So, given B has happened, I have only 4 events. Out of them, what is the probability that AO, that is my favorable case, will be happening? That is actually 2. So, it is 2 cross 2 by 4 into probability of B. How much is that? That is again same thing, probability of B remains the same, 2 by 3. So, that is 1 by 2. So, I get the same result, which says yes, these two events are independent. I just change this definition, I change the definition of B. I say my B is this, you will see a fantastic thing happening. If my B is this, that means B, that event B is actually less than 5, less than equal to 5 happening. Okay. So, let us try to do that same calculation. If they are independent, what should be this? PAO, that is actually 3 divided by 6. So, that is again 1 by 2, and PB, that is actually 5 divided by 6, right. So, if they are independent, this is the case, right. Now, let us see if they are not independent. So, what do I get? I do get over here B has already occurred, okay. Out of them, how many are AO? That should be 3 by 5 multiplied by PB, which is 2 by 3. See, the probabilities are not same. So, the event, whether it will be independent or not, it all depends on whether this is equal to this. Probability AO given B is equal to probability AO that I can evaluate. Okay. So, if that is not happening, that means the events are not independent. See, whenever I was taking 4, because what was happening actually, because it was taking same number of odd and even. So, eventually, or half of them were even. So, eventually my independency was coming out. Whenever that has not happened, because I have taken now 5 number, so there is a bias towards odd event. Okay. Once that has happened, immediately my independency goes away. So, why I have given this example? A slight definition of the event or slight variation in the definition of the event can change your dependency. So, you have to be very careful whenever you are writing a joint event to be the multiplication of 2 events. So, whenever you do that, you have to be very careful, you have to ensure that that is the case, otherwise you will be doing a mistake. This is more generic definition with a conditional probability. So, always you should take that into account. Okay. So, now let us see, we have already defined P, let us just go back from that example, let us just take 2 things. 2 events A and B. So, A intersection B, we have said it is P A given B into P B. Okay, these 2 events, I have no preference. So, I can even write this as P B given A into P A, there is no problem in that, because I can just replace A by B and B by A, I get the same formula, right. So, these 2 are equal, and immediately I can see that P A given B can be calculated, because these 2 are equal. I can always calculate B given A, P A divided by P B. That is the famous Bayes theorem. Okay. So, what we are doing, we are just building up the probability theory, entire probability theory, just from that initial frequency postulate. With that only we defined all these things, and now we are getting one after another theorem. So, these are all linked, and they have some importance also. We will later on see why this is very important. Okay. So, we will talk about that later on when we give more generalized thing. So, now I would like to touch on 2 things. Okay. We have now talked about 2 particular kind of event. One is independent event, one is mutually exclusive events. Are they same thing or are they not? Okay. Basically, it is not, they are completely different. Do not confuse independent event with mutual independence, or mutual exclusiveness. In mutual exclusiveness, what we are saying, just take that example of AO and AE, odd and even. In that case, if AO happens, that means the odd number I get, immediately I can say that even will not be happening. So, basically I am almost saying there is a strong dependency. Instead of becoming independent, mutually exclusive events are strongly dependent. If I say this event has occurred, that actually means the other event has not occurred. So, I have already some understanding of the other event by defining this event. Okay. So, they must be strongly dependent. So, mutually exclusive events are never independent. Mutually exclusiveness has nothing to do with independence. People often get confused with these two definitions. They start thinking that mutually exclusiveness is probably also defining independence. No, it is not. That is the mistake people do often when they are just starting to learn probability theory. So, that is not the case. In mutually exclusiveness, remember the probability axiom that if two events are mutually exclusive, then I can write this. And if two events are mutually independent, suppose A and B, then I can write this. So, always remember this. And if two events are not mutually exclusive, then I can write, suppose A union B, I wish to write. So, that must be set theory we know, P A plus P B, we have already talked about that. It will actually count 2 times. So, I have to take this out. If they are independent, but not mutually exclusive, then I get this theorem. This happens. Okay. So, the two events A and B are independent, but they are not mutually exclusive, then this should be happening. If they are mutually exclusive, this should be 0. Okay. So, whether they are independent, they are not independent, means actually mutually exclusive means they are not independent. So, and this immediately happens to be 0. Okay. So, that is something which we should be keeping in mind whenever we are defining probability. Now, let us do something more. Okay. Just take the Bayes theorem towards more generic one. Okay. So, let us say I have a event B. Okay. So, this is the sample space of B, let us say. So, in between all those events are actually, or all those elements are included. And this sample space, I now actually include it within a particular sample space called A, and I divide that A into some mutually exclusive partition. Okay, I call that A1, A2, A3, A4 and so on. Okay. So, what I have done is I have taken this B, I have taken a superset of B, okay, which is A, and then I have actually partitioned A in mutually exclusive parts, okay, and I am calling them AI. Okay. And what I am saying that this A actually happens to cover the entire sample space that I am experimenting with. So, that means all the events that can happen, that is included in the entire A. Okay. So, A include everything in that sample space, B might not, because B is a subset of A. So, B might not include that, but A include everything. So, I can always write union of AI, because they are mutually exclusive. So, they will be just added one after another, or their elements will be just added over I if I add them. So, that must give me the overall sample space, that is according to definition. Okay. And I also have this definition, AI intersection AJ is null set for all I not equal to j. Okay. So, this is the definition of my A, that is how I have created my A. Now, what I can write about B? See, B, because B is a means proper subset of A or that sample space S, I can always write B equal to this, because it will have, see, when I take, if it is a proper subset, the elements of that will be actually elements of that and intersection of the bigger set, because it will have the same elements, right. So, I can write this. Now, S I can substitute with this one. So, it should be B intersection union of AI. Okay. So, now because they are mutually exclusive, I can actually just flip these two. So, I can write this as which is very obvious from the Venn diagram also, the diagram I have drawn. So, B I can write as this plus this, where this is actually B intersection AI or A1. This is actually B intersection A2. If I just add all of them, I must be getting B back. So, this is what is happening. So, union B intersection A, suppose it goes up to n. So, n. So, I have made n partition, here it is n equal to 7, right. So, I can write this. Now, because AIs are all mutually exclusive, so the B intersection AIs are mutually exclusive. That is very obvious from here also, they are all mutually exclusive because AIs are mutually exclusive. So, if I take B intersection AI, that must be a subset of that. Now, B intersection A1 and B intersection A2, if A1, A2 are already mutually exclusive, they have no common element, therefore, that small subset must not have any common element. So, I can always write these are all mutually exclusive. So, now probability of B, what can I write? That should be probability of this whole thing because B is this. Now, because they are mutually exclusive, now I put that probability theorem of mutually exclusiveness. So, that should be sum of all those probabilities. So, I can just write summation over I going from 1 to n, it is P B intersection AI, right. I can write this, no problem in that. Now, I can put Bayes theorem the way I have learned it. So, I equal to 1 to n, this intersection is, I can write it in terms of conditional probability. So, I can write P B given AI into P AI. That is something which I can write now. Okay. P B, that event we were talking about, which is a subset of that whole thing, must be this. So, eventually what happens? I have earlier proven that P sum AI given B, or let us say, let us just put J because I will be putting a dummy variable. So, this is something I have already proven that that should be P B given AJ P AJ divided by P B. Now, just now I have proven P B should be a summation term. So, I can just write this as given AJ P AJ divided by summation I equals to 1 to n P B given AI that is the most generic form of Bayes theorem. Okay. You might be asking why we are doing this, why Bayes theorem is so important. Okay. So, what we should do is we should give some example of these things, okay. That whatever we are doing, that is very important. But before giving that example, probably we will have to now go into another definition. Once we get means our hands very clear on that definition, probably it will be easier to give that example. We'll pick one very important communication example to say why this is very important, okay, why we are actually learning Bayes theorem. As a communication expert, why this is very important for us, okay. But before that, let us try to do something. Let us try to give another definition, which is very important to probability theory, which is called random variable. So, what do I mean by random variable or RV? See, so far we have been talking about set, elements, events. Events are like if I roll a die, it is just a description, right. It is the top surface getting 1 or top surface getting 2 and all those things. Mathematically, those are not, that description is not very sound, right. I cannot represent them mathematically, I cannot write anything over there, okay, in terms of mathematical equation and all those things. So, it is very important that we define those things into a sound mathematical background, okay. And that is where random variable comes into picture. So, basically random variable is nothing but mapping those abstract things of definition of events into the real axis, okay. So, suppose I have head and tail, these were two outcomes of tossing a coin, okay. So, this was an abstract thing, it is just a word, that head or tail, it has no mathematical notion, it does not go into some number and all those things. So, I cannot really manipulate them. So, now what I do a mapping. I say that head gets mapped to -1 in the real axis and tail gets mapped to +1 or vice versa, whichever way you wish to put it, okay. So, if I just do that, then I get a definition of random variable. So, because this head and tail were actually random outcome, the event is defined, but I do not know if I do the experiment whether I will be getting head or tail. That is why I call it random, because beforehand, before doing it, I have no notion of or no understanding what will be the outcome of that experiment. So, I cannot say that, but what I can actually define is probability of those. That means, what is the chance of getting head? I can define that, that is what we have defined so far. So, probability of that event I have already defined. So, I have said probability of head is actually half, and I have said probability of tail is actually half. This is something I have told. Now, what I will do, instead of saying probability of a event which is abstractly defined, I will say probability of this +1 and -1, and I will put some number. Immediately what do I get? I get a functional representation of this probability. So, what I do, this head I put it to some discrete value which I have done this -1 to the real axis. So, I call it x1. So, x1 is equal to -1, and tail I put it into the real axis. I call this x2, okay, which is a real number. So, x1 and x2 are taken from the real number, okay, set of real number. So, x2 is +1, it can be anything, either you give -1 +1, I can also give 0 and 2, 0 and 5, whatever you wish you can give that, but as long as your definition is clear, you know that it will be mapped as a function, okay. So, at -1 this will have a value of half, and at +1 it will have a value of half, and the associated function is defined as PMF or probability mass function. It is actually defining that if I map uniquely, this must be one-to-one mapping, remember, every event should be uniquely mapped to the real axis. There should not be any ambiguity. If head and tail I map to the same point, I will just get half plus half 1, and I will not have any distinguishing feature between head and tail, whereas actually they are two different events. Okay. So, I need to have a one-to-one mapping to the real axis, and then I plot the probability with respect to them. Whatever I get, that I call as probability mass function. That means, in the real axis, as if that is representing the random variable that I am describing by doing this mapping. Okay. And here, because I have countable number of events, so that is why the overall mapping will be discrete mapping, remember. If a random experiment gives me uncountable number of events, then I can actually map it to a continuous variable. Whereas, if I have countable number of events, I will only be mapping them to a finite number of, or if not finite, at least countable events, and they will be all discrete. So, I get discrete probability values, and the associated function I call it probability mass function. Okay. You will also see the other definition of it, whenever I will have continuous one, we will have probability density function, but this is called probability mass function. Okay. Fine. So, this definition is there is no problem in that. Okay. So, how do I define this? So, I say the associated random variable is x, and this x might take value. Now, we are defining, earlier we were saying just head or tail. Now we can say this takes value x1 or x2, right, if it is head tail. If it is a die, I can write it is x1, x2 up to x6, right. If it is any other experiment, suppose it is card, so there will be 52 such elements, right. So, it depends on what kind of experiment you are doing, accordingly how many events are there or elements are there, they will be all mapped to a real axis, and those becomes the random elements. So, I define a random variable x and those have elements x1, x2, x3, and then the PMF I define it this way: P probability of this random variable taking a value x1, okay, or you can put first bracket as well. So, this actually says that your random variable, okay, which is this x defined by this x, this is a random variable, it takes a value x1, what is the associated probability. So, if I am doing this experiment, this must be half if x1 is defined as head, and px x2 that becomes half, okay, that is all. If this is the random experiment, then I call px x1 that should be 1 by 6 and so on, all of them will be 1 by 6. Okay. So, that is how I define it, and that is how I get the probability mass function. Similarly, I can start defining the joint event. Okay. So, the joint event will be, it's like this. So, let us say I put a value xi and yi. So, this is the definition of joint event. That means, basically now I am trying to see a probability that two random events or two random variables taking correspondingly value of x1 or xi from the random variable x and y1 from the random variable y. This is the associated joint probability of x and y simultaneously happening, which are taking simultaneously value xi and yi. Okay. So, this is the definition of the joint probability. What we will try to do next is probably we will try to give the axioms of these things now in terms of random variables. So far we have defined in terms of set theory and events only, but we have not mapped it properly to the random variable. Now we will actually properly map it to the random variable, which we have just started. We will do all those axioms, we will actually map it to proper random variable and then try to see what is the outcome of them. Okay. And then from there we will go towards the definition of continuous random variable. Okay. Thank you.